Hello, my name is Karan Jain and I am a PhD student in the High Performance Robotics Lab at UC Berkeley, advised by Professor Mark Miller. Today, I'm going to talk about my research titled Staging Energy Sources to Extend Flight Time of a Multi-Rotor UAV. I believe most of us have seen a multi-rotor before. If not, a picture of one is shown on the right. They are used in the industry for a variety of applications such as surveillance, mapping, imaging, owing to their ability to hover as a compact machine and carry useful sensors. However, this hovering ability comes at the cost of reduced endurance and range as compared to their fixed-wing counterparts. Typical commercial multirotors have flight times of about 15 to 30 minutes. There is a demand in the industry for uninterrupted missions and longer range for applications such as package deliveries. One of the problems is that the energy sources used by multirotors, such as batteries, do not reduce in mass and remain as dead weight after consumption. Moreover, the energy source mass is typically a significant fraction of the total mass. We look at rocket staging for inspiration. Shown here are videos of a space shuttle and a Falcon 9 detaching their booster stage after consumption. This is done to remove the dead mass and further increase the delta V for remaining stages. Can we do something similar for drones? Yes, we can, and that is what will be covered in this presentation. This video shows a quadcopter ejecting its first stage battery. We attach a parachute to the ejected stage to avoid damage to the battery and the surroundings. I would like to emphasize that staging of energy sources for multirotors is fundamentally different from rocket staging in two senses. First, rocket staging is about discretely staging the structure and not the energy source itself. Second, the power consumption model is different in the two cases. So, what do we want to achieve? We want to extend the flight time of a multirotor without landing it. This is an absolute necessity for uninterrupted missions, and hence the operation has to be in flight. What are the possible methods to do this? The most obvious solution might be to add more battery. That, however, adds mass and more so to the power consumption and is usually not an optimum approach. Other possible methods are to increase efficiency through novel mechanical or electrical design. Our approach is to use the energy source in multiple stages instead of in one go. Each stage has to be ejected after consumption to reduce the vehicle mass, which reduces power consumption and consequently increases the overall flight time. Here is an outline of this presentation. We will start by going through the power consumption model of a multirotor and derive the flight time with respect to the energy storage mass for various number of stages. We will then cover two optimal staging problems with the objective being maximization of flight time. Then, we will cover a limiting case of staging, namely continuous staging. Secondly, we will show experimental validation of the staging analysis on a custom designed two-stage quadcopter. Lastly, we will go through the environmental concerns of staging and the special cases in which staging can be utilized. Let us begin by deriving the flight time for a regular single-stage multirotor. Based on the actuator disk model, we claim that the power consumption of a propeller is proportional to the thrust raised to 3 halves. So, for a multirotor in hover, the power consumption can be modeled as its mass raised to 3 halves. The energy contained in the onboard energy source is the specific energy, EB, times its mass. Throughout the analysis, we will assume that all the stages have the same specific energy. We can now claim that the flight time is the ratio of the total energy to the power consumption, which is assumed to be constant in hover. Ct here is a vehicle-specific constant and depends on the powertrain efficiency, propeller size, etc. We note that this constant is independent of the vehicle mass. Let us now generalize the flight time equation to a multirotor with n stages. The dry mass of the vehicle, that is the mass of everything on the vehicle except the energy sources, is denoted by md. The stages are labeled 1 to n such that the first stage is consumed and ejected first, and so on. Mass of the ith stage energy source is denoted by mi. At the ith stage, the vehicle has ejected the first I-1 stages and its total mass is given by equation 1. So the flight time contributed by the ith stage is given by the formula for a single stage case with the energy storage mass mi. This is shown in equation 2. The total flight time is simply the sum of the respective flight times of each stage as shown in equation 3. We now consider the optimal mass partitioning problem. Here, we are given a total energy storage mass budget MB and we want to partition it into n stages so as to maximize the flight time. We have two constraints here. The first being that the mass of any stage needs to be positive, and the second is that the masses of all stages should add up to the mass budget. The decision variables are the masses of the individual stages. On looking at the objective, we see that the decision variables are involved in a nonlinear way and in a lot of terms. We reformulate the problem with new decision variables xi's, which are essentially the total mass of the vehicle at the ith stage. This also means that the mass of the ith stage is given by xi minus xi plus 1. The objective now reformulates to the expression as shown by J. The nice thing about this objective is that each term just contains two decision variables and is easier to solve analytically. We formally write the optimization problem. The constraints are physically intuitive. At the first stage, the total vehicle mass is the sum of the dry mass and the total mass budget. At the n plus 1 stage, only the dry mass remains. And the vehicle also gets lighter with each ejection. So total mass of the vehicle at stage I plus 1 will be lesser than at stage I. This is solved analytically using the KKT conditions, and we obtain a solution in the form of simultaneous nonlinear equations, n plus 1 equations for n plus 1 variables. These in general have to be solved numerically because they involve a fifth degree polynomial for which no general analytical solution exists. We will now go through the limiting continuous case of staging. Essentially, the energy source is continuously consumed and ejected. An example of this would be a combustion engine which exhausts its fuel continuously on consumption. The governing equation is now a differential equation, where the rate of change of mass equals the power consumption divided by the specific energy as shown in equation 1. This can be integrated with the limits me equals to the total energy mass mb at time t equals 0 and at time equals the flight time me equals 0. That is, all the energy has been consumed. This gives us the flight time formula shown in equation 2. A very interesting point to note is that even if we use an infinite amount of fuel, that is in the limit of mb going to infinity, we still only get a finite flight time, which depends on the specific energy, dry mass, and other vehicle specifications included in CT. We can summarize the analysis covered until now in a single plot as shown. On the y-axis, we have the flight time normalized with respect to that in the continuously staged case with infinite energy storage, namely TF infinity. On the x-axis, we have the ratio of the energy storage mass to the total vehicle mass. Note that this scale is highly nonlinear and encompasses all possible values of mb from 0 to infinity. The solid blue line shows the flight time of an unstaged or single stage case. We then have several solid lines representing equally staged case, that is, each of the stages weighs the total energy mass divided by the number of stages, as shown by equation 3. The solid black line shows flight times for the continuously staged case, the formula for which is given by equation 4. Lastly, we have dashed lines showing the flight times for the optimally partitioned case for different number of stages. We can clearly see that the optimal partitioned case always performs better than the equally staged case. Moreover, the flight time increases monotonically in the number of stages for both equally staged case and optimally partitioned case. We will now consider our second optimal staging problem, which is, given n energy storage stages of known masses, how can we maximize the flight time with respect to the order in which we use these stages? The solution turns out to be a simple one. We should stage in order of decreasing mass, that is, the heaviest stage needs to be ejected first. The solution is proven by contradiction. We consider that someone has given us an optimal staging sequence S star, but in this sequence, for some value of k, the kth stage is lighter than the k plus 1 stage. Let us call the corresponding flight time T star. We can now consider a modified sequence S bar, where the only modification is interchanging the kth and k plus 1 stage from S star. The new flight time is now T bar. Using the flight time equation derived earlier, we can show that T bar is actually higher than T star, arriving at a contradiction. So in an optimal staging sequence, we can never have two consecutive stages such that the earlier stage is lighter, and the only way to meet this condition is to have the stages in order of decreasing mass. Let me quickly summarize the takeaways from the staging analysis before going into experimental validation. We showed that using an energy source in stages improves flight time. We considered the optimal partitioning problem and derived the solution in the form of simultaneous nonlinear equations. We then showed that even if we continuously stage the energy source and use an unlimited amount of energy source, we can still only get a flight time which is finite. Lastly, we proved that if one were to maximize flight time based on the staging order, then the heaviest energy source should be staged first. We now present our hardware design. The vehicle that we use is a custom designed quadcopter with a dry mass of 565 grams. It can use two 3S lithium polymer batteries either simultaneously or successively. It can also eject the first stage battery in flight. It does so by using a staging mechanism, which works on a simple mechanical principle. The first stage is attached to the quadcopter via a screw and a support. We can eject the first stage by turning a motor which is connected to the screw. The stage then loses support and falls under gravity. I will show a video of this shortly. For the battery switching circuit, we had two requirements. Firstly, we cannot afford to cut power since we have a flying system. So at some point the two batteries need to be connected in parallel. We avoid the batteries discharging into one another by adding diodes in series with each battery. To actually switch the power source, we use an electromechanical relay in series with the first stage battery, which is controlled via our flight controller. Before the experiments, let us see the predicted flight times from the analysis. We use the parameters shown on this slide, which are obtained from datasheets or experimentally. Then using this formula, we predict flight times of about 19 minutes for the single stage case and about 23 minutes for the two stage case. We show a video of the single stage and two stage hovering flight side by side for a convenient comparison. In both cases, the quadcopter takes off and starts hovering. In the single stage case, it is consuming both batteries simultaneously. In the two stage case, it is consuming the first battery first. The first battery discharges around 9 minutes into the flight and is ejected via the mechanism as can be seen in the onboard video. From this point onwards, the two stage case uses the second battery only. The single stage case discharges around 19 minutes and lands. Meanwhile, the two stage case continues hovering for about 23 minutes before completely discharging the second stage. We repeated the experiment 3 times for both cases, and the average observed flight times match really well with the predictions, with less than a 5% error. The observed standard deviations in the flight times were about 0.2 minutes in each case, which suggests that the experiments are pretty consistent. On the right, we can see the input voltage and power plotted with respect to time. In the power curve, we see a clear decrease after ejecting the first stage. Since the total energy is the same, the two-stage case clearly gives a higher flight time due to reduced power consumption. I would like to show a video of the quadcopter ejecting the battery while performing a maneuver to show that ejecting a stage has a negligible effect on the maneuver itself. Note that we adjust the physical parameters such as mass and moment of inertia when the ejection command is received. Let us now look into the use cases of the staging concept. Ejecting energy sources such as batteries out in the open is not a good idea because it can have adverse impact on the surroundings, even with the use of a parachute. Moreover, the discarded stages are usually reusable and hence an effort should be made to retrieve those. Hence the use of staging will most likely be restricted to specialized cases. One example is long duration surveillance of industrial sites where there are no third parties involved. Retrieval is also easy here because the user will typically own the space of flight. Another use could be in the case of natural disasters where the immediate benefit of a longer flight outweighs the potential negative environmental impact. We could also have uses in exploration of extreme environments such as those of other celestial bodies. Drones have been increasingly considered for exploration of these environments, and NASA, for example, already has missions planned for exploration of Mars and Titan with aerial vehicles. To conclude, we presented the concept of staging, where we use the energy source in multiple stages and eject each stage after consumption. We also carried out an analysis to predict the flight times for a multi-stage vehicle with given energy storage parameters. We then considered and solved two optimal staging problems to maximize the flight time, namely the optimal order of staging and optimal mass partitioning. The limiting case of continuous staging was covered and we observed a fundamental limit on the flight time regardless of the amount of energy. We then experimentally validated the staging analysis on a custom designed two-stage quadcopter which can eject a stage in flight. We observed a 19% increase in flight time when using the batteries in 2 stages instead of 1. Lastly, we addressed the potential environmental concerns of staging and saw the specialized use cases which can benefit from staging. Some of the possible extensions to this work are also listed. We could have additional stages on the quadcopter which would entail a more intricate design of the staging mechanism and the switching circuit. Another extension could be the planning of stage ejection locations for easy and automated retrieval of these ejected stages. Thank you.